So, hello everyone on YouTube as well. Today is the ninth discussion on Measure and Integration course by NPTEL, and today I plan to continue what we started last time. That is looking at some functions, non-negative functions, and asking whether they are integrable or not by approximating them using simple functions. So, the general technique we have already seen how to do it during the class, but let me just recall it once again. That given a non-negative function or non-negative measurable function rather, given f in L plus, which is the set of all non-negative measurable functions, what we want to do is we want to approximate it using simple functions. So we define Sn as sum over k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi of f inverse k minus 1 by 2 to the power n to k by 2 to the power n, well, open towards the right, plus n times chi of f inverse n2 plus infinity. So then it is easy to see that Sns are actually in L0 plus, that is, they are non-negative simple measurable functions. And Sn converges to f pointwise. Moreover, we define the integral of f with respect to whatever measure we have on our measure space x as limit n going to infinity integral Sn d mu over x, where further this integral Sn d mu, this was defined as the sum of areas of the rectangles given by these characteristic functions, particularly the k minus 1 by 2 to the power n into measure of f inverse k minus 1 by 2 to the power n to k by 2 to the power n plus n times measure of f inverse n2 plus infinity. So again, if we are to recall it geometrically, what we are trying to do is, let us look at a function. Perhaps the function is this. This is our f, and we want to integrate it. So we are going to split our codomain into equal parts, or rather not so equal parts, but 0 to n first. Let us split it open here at n, and then from n to plus infinity, let us keep it as a one interval. So on this n to infinity, let us draw a line here, and wherever it intersects f, let me just make it a solid line. So this is our f inverse n2 plus infinity. On this region, the value of our Sn is n. Now, in this smaller interval 0 to n, we are again going to divide it into 2 to the power n equal parts. So, like not only this, so first let us divide it from 0 to 1, from 1 to 2, and so on. And each of this interval of length 1, I'm going to divide it into further parts, 1 by 2 to the power n, and so on. Again, let us draw lines everywhere, and wherever these lines intersect f, yeah. So there I'm going to sort of do this. So here the value is this much, here the value is this much, and so on. So in this way, we get simple measurable functions that can approximate f very nicely. And since we want to define this integral of f, that means the area under f. So what we do is, let us look at all these small rectangles and let us add all their areas. We expect that it should give the total area of f. So we define integral of f as limits of integral of Sn. Now, So last time we had already discussed a few examples. Particularly, we saw that chi q is in L1 mu or L1 lambda, and integral of chi q d lambda over r, this is 0. That is because rationals are countable, and chi q is just a simple function with one set. So this integral is actually the measure of rational numbers, which is 0. Another example which we saw last time was this function from r to r, given by fx is 0 when x is less than or equal to 0, and it is 1 over x when x is bigger than 0. So it looked like this. In the positive quadrant, it is 1 over x, while on the negative x-axis, it is 0. So we have seen that this f, although it can be approximated using simple functions, it is also measurable because it is continuous almost everywhere. But f is not in L1 lambda, and any truncations towards 0 or plus infinity are not in L1 lambda. That means if I just want to look at this function from epsilon to plus infinity, this is not in L1 lambda. Or if I want to look at, say, 0 to m, this green function, even then it is not in L1 lambda. Unless we restrict it to a closed and bounded interval or open and bounded interval for that matter, this f will never be in L1. That is what we saw. That was because the idea was that the rectangles which were obtained using f inverse, those areas were getting larger and larger, and we were getting the harmonic series, which we know is divergent. Okay, so we continue looking at more examples of easy to see functions. Most of them will be continuous. One of them is not continuous, that we'll see later. And we'll try to approximate it using simple functions. And then we'll try to see whether it is integrable or not. If it is integrable, what is its value of the integral? That means what is area under its curve. So let us start with an example. Let us look at this function f from r to r, defined as fx is mod x into chi of minus 1 to 2. And this is closed and bounded interval. So how does this function look like? Let us first draw. Let us try to see whether we can calculate its area using simple geometric tools, because this function is really easy to see. It is mod x, so it may consist of two triangles, and we know how to calculate the area of triangles using simple geometry. So somewhere here is minus 1, somewhere here is 2. This is our 0, and this is 1, this is 2. So the function starts here, it goes to 0, and the function would end here. Everywhere else, before minus 1 and after 2, the function is 0. So it is not going to contribute to the area under the curve. What is going to contribute is these triangles formed by, well, the green lines and the red dotted lines. And we know how to calculate it. So the area of left triangle is half into base into height. This length is 1, this length is 1, and this length is 2, this length is 2. So total area is half into 1 into 1 plus half into 2 into 2, which is half plus 2, which is 5 by 2. So we expect that since Lebesgue integrals are generalizations of Riemann integrals, and Riemann integrals are, the motivation of Riemann integral is area under a curve, then we expect that the Lebesgue integral of this function mod x into chi of minus 1 comma 2, this should give us 5 by 2. So what we expect? We expect that f is inside L1 r lambda, and integral of f d lambda over r is equal to 5 by 2. Notice that this is a truncated function. If it were not truncated at any side, for example, if it were minus infinity to plus 2 or minus 1 to plus infinity, then it would not have been integrable. At least we would not expect it to be, because then one of the triangles should be infinite and hence it would have infinite area. So let us see whether such a thing is really happening in our case. Again, what we want to do, we want to approximate this f using simple functions. So the general formula is k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi f inverse of, excuse me, chi f inverse of k minus 1 by 2 to the power n to k by 2 to the power n, plus n times chi f inverse of n2 plus infinity. Now there is a thing to notice, that since this is a bounded function, after a certain time this is not going to contribute. Does not contribute, in particular for n bigger than or equal to 2. Because once n is bigger than or equal to 2, or okay, let us see what happens. First, let us see what happens when n equal to 2. For n is equal to 2, f inverse of 2 to plus infinity. This is the collection of all real numbers such that mod x into chi of minus 1 to 2x. This is bigger than or equal to 2. But this is just a singleton element 2. And therefore its measure is 0. Even if this n is not 0, then finally under the integration of Sn, this does not contribute. And for n bigger than or equal to 3, f inverse of n comma plus infinity, this is empty. Because f does not take values beyond 2. So after a certain stage, this is not going to matter. So we may very well exclude it from our calculations. Of course, while writing S1 and S2, we might require to write it. But since we are going to take limits later on, we may just exclude it altogether. Now, so since this is empty, which means chi of empty set is actually identically 0. So it doesn't give anything in the integral. Now let us do this essence, compute this essence for say n equal to 1 and n equal to 2. We'll see how do we get these step functions here, and then for arbitrary n we'll directly write it. So S1, this is k from 1 to 2, k minus 1 by 2 to k minus 1 by 2, chi of f inverse of k minus 1 by 2 to k by 2 plus chi of f inverse of 1 to infinity. So let us again draw this figure and let us try to see where these sets are. So one goes from 0 to 2. The another is only from minus 1 to 0. Somewhere 1. So this is 1 and this is 2. And beyond minus 1 and 2, the function is 0 as it is. Okay. So first thing, f inverse of when k is equal to 1, f inverse of 0 to half. This is, look at all those x in minus 1 comma 2 such that mod x is less than half. It is already bigger than or equal to 0, so we don't have to worry about it. So we want to look at all those x such that mod x is less than or equal to half, but we know what that set is. That set is interval minus half to half. So on this open interval, minus half to half, we have 0, right? The value is 0. What about the next interval? It is for k equal to 2. So f inverse of half to 1. That is, look at all those x in minus 1 to 2, close to, such that half is less than or equal to mod x, and at the same time mod x is strictly less than 1, which is union of two intervals particularly from open -1 to closed -half, and for closed half to open 1, which are, well, these closed half to open 1. And here we have the value. What is the value here? Put k equal to 2, so that will be 1 by 2. So here we have, this must be half. So here we have 1 by 2. Here we have 1 by 2. Okay. Let me just run this as well. Here as well. Now, what about the other term? It is from f inverse of 1 to infinity. F inverse of 1 to plus infinity. It is the collection of all elements in -1, 2, such that mod x is bigger than or equal to 1. Or what is the same, I can write it as, well, notice that here, either it is -1, in which case mod x is equal to 1, or it is in between closed interval 1 and closed interval 2. So it is -1 union 1, 2. So that means either this point or this interval. So this is our S1. Similarly, we can write S2. It is easy to see. It will be from 1 to, now n is equal to 2 here. So it is 2 times 2 square, which is 8. Is it so? Yes, it is 2 times 2 square, which is 8. A minus 1 by 2 to the power n. Chi of f inverse k minus 1 by 2 to the power n. K by 2 to the power n plus n times chi of f inverse k minus 1 by 2 to the power n. Oh, no. This would be from n to infinity, n to plus infinity. Now, of course, it is easy to calculate, but there are 9 intervals, so we'll not be doing here. If you are enthusiastic about it, one can try and one can try to plot it. What I would rather do right now is, let us, instead of looking at S2, let us look at Sn in general, and let us try to calculate what these sets are. That would give us an idea. So I have already said that for n bigger than or equal to 3, this is 0. This is 0 for n bigger than or equal to 3. So we only need to compute this. So f inverse of k minus 1 by 2 to the power n to k by 2 to the power n. This is, look at all those x in -1, 2, such that k minus 1 by 2 to the power n is less than or equal to mod x, and mod x is less than k by 2 to the power n, which is clearly the union of two intervals, namely minus k by 2 to the power n to k minus 1 by 2 to the power n, minus of this, closed here, union k minus 1 by 2 to the power n closed, k by 2 to the power n open. So in general, Sn is sum k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi of minus k by 2 to the power n to minus of k minus 1 by 2 to the power n, closed here, union k minus 1 by 2 to the power n to k by 2 to the power n, and plus 0. So I am going to write this for n bigger than or equal to 3. And notice that this is a disjoint union. So finally, when I look at the measure, it is going to be the sum of the individual measures. Disjoint union of intervals, which means the length of the total union is actually length of the first interval plus the length of the second interval. Now, so we have already written this. Let us now compute S and d lambda over R. This is summation k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, and then the length of minus k by 2 to the power n to minus of k minus 1 by 2 to the power n, union, closed here, and k minus 1 by 2 to the power n to k by 2 to the power n. which is k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n. Now, what is the length of the first interval? It is minus of k minus 1 minus of minus k whole over 2 to the power n, plus the length of the second interval is k minus 1 upon 2 to the power n. They are equal intervals, so the lengths are going to be the same. Particularly, the length is 1 over 2 to the power n here. So it is sum from 1 to n into 2 to the power n, k minus 1 by 2 to the power n into 2 over 2 to the power n. Yeah, is that correct? Yes. Yes. Oh well, it is not quite true. Yeah, I'm so sorry for this. It is not quite true. Let me just erase it, and because I have missed one thing, this function is not really symmetric. If you look at the graph here, then on the left hand side of 0 it goes up till minus 1, but on the right hand side it goes up till 2. So there would be two different cases. So this is only true when k by 2 to the power n is less than or equal to 1, or what is the same, k is less than or equal to 2 to the power n. Or perhaps if we want to write it, should I write it as 2 to the power n? Yeah. Even at when k is equal to 2 to the power n is less than 1. Yeah, that this is correct. On the other hand, if k is bigger than k by 2 to the power n is bigger than 1, we'll get a different representation. So if inverse of k minus 1 by 2 to the power n to k by 2 to the power n. So when we move beyond 1, only the right part remains. So that would be k minus 1 by 2 to the power n to k by 2 to the power n when k is bigger than 2 to the power n. Okay. So with this understanding, oh, okay, yes, that is correct. With this understanding, now let us write Sns. Sn is k from 1 to 2 to the power n, 1 to 2 to the power n, and then what will happen to this? K minus 1 by 2 to the power n, pi of minus k by 2 to the power n to minus of k minus 1 by 2 to the power n, union k minus 1 by 2 to the power n to k by 2 to the power n, plus now the remaining terms 2 to the power n plus 1 to where would it go? Up till 2 it would be give something, but beyond 2 it is again going to give us the empty set. So it would go up to 2 into 2 to the power n. And there it will again be, the value is same, k minus 1 by 2 to the power n, but the set is different. The set this time is just one interval, k by 2 to the power. And therefore the integral of Sn with respect to the length function over R is equal to k from 1 to 2 to the power n, k minus 1 by 2 to the power n, the length of this thing. So it is 2 by 2 to the power n as we discussed before, plus k from 2 to the power n plus 1 to 2 into 2 to the power n, the length of this interval, which is 1 by 2 to the power n into k minus 1 by 2 to the power n. Well, and now it is just a matter of computation. So after using the formula for summation of k's from some point 1 to n, the sum of first and natural numbers, one would get 1 by 2 to the power n into 5 by 2 into 2 to the power n minus 3 by 2, which is 5 by 2 minus 3 over 2 to the power n plus 1. So from here to here, it is just a matter of computation. Okay, and therefore, what we have is integral of f d lambda, by definition, is limit n going to infinity, integral of Sn d lambda. And notice that the other term goes to 0, 5 by 2 remains, that is 5 by 2. As expected, as we were expecting it, that the area under the curve would be 5 by 2. So by all the methods, by using simple geometry, by using the Riemann integral technique, and now by using the Lebesgue integral technique, we get the same thing. So this is also a example which shows that Lebesgue integration is indeed a generalization of the notion of integrals, which were in turn generalization of the notion of area under functions. Okay. So this is one thing. Now let us look at one example where making the graph of the function is not very simple. In fact, I would say that we are not able to make the graph because the function is defined differently for rationals and irrationals, just like the Dirichlet function. But it was easy to see because it was a simple function. Now what we are going to define is not going to be a simple function. We would have to approximate it using some type of simple function. Let us look at this example. Let us define f from R to R as follows. F at any point x, this is 0, when x is either bigger than 1 or x is less than 1 or x is a rational number between 0 and 1. And define it to be n if x has, first of all, it should not be a rational number in between 0 and 1. You complement intersection open 0, 1, because notice that 0 and 1 are already rational, so they are counted in the above case. And the first non-zero entry in the decimal expansion, the first non-zero entry in the decimal expansion of x is at the n plus 1th place. So for example, if we start with something as 1 over pi, this is, it is, since pi is between 3 and 4, okay, so let us try to see what this is. I know that pi is bigger than 3 but less than 4. So 1 by 4 is bigger than 1 by pi and 1 by pi is less than 1 by 3. And this is 0.33. This is 0.25. Yeah. So the first, since it is in between these two, the first non-zero entry in the decimal expansion of 1 by pi must be at the first place, which means f of 1 by pi is equal to 2. But if I start with pi square now, pi square is less than 16 but bigger than 9. So 1 over pi square is less than 1 over 9 but bigger than 1 over 16. 1 over 16 is, what will it be? The square of 0.25, which is 0.0625. And this is around 0.11. Okay, so we'll have to see whether 1 over pi square has a non-zero entry in the first place or not. So either f of 1 over pi square is either 2 or 3, depending on whether it has non-zero entry in first or second decimal case. And one can continue looking at it. Of course, looking at irrational numbers is much more difficult than looking at rational numbers. And we have by force defined the images of all rationals between 0 and 1 to be 0. So, but even still, if I want to, look at this function, how does it look like? Then what I would rather do is let us try to draw a figure, but we'll not be able to plot the graph. We'll at most be able to estimate this using the rational numbers that we know. So let me now draw like this. Since we are only looking at the interval 0, 1, let us just isolate that 0, 1. So this is 0, this is 1. And before 0, everything is 0. After 1, everything is 0. At rational numbers between 0 and 1, everything is 0. That means at 0, the value is 0. At 1 also, the value is 0. Now I want to estimate what happens in between. So what I would rather do is, let us divide this 0, 1 into intervals of the form 1 by 10, then 1 by 10 to 1 by 100, 1 by 100 to 1 by 1000, and so on. So it will be 1 by 10, 1 by 100, 1 by 1000, 1 by 10 to the power 4, 1 by 10 to the power 5, and so on. So notice that any number between 1 by 10 and 1 always has a non-zero digit at the first place in the decimal expansion, because 0.1 itself has a non-zero digit in the first place. So every number bigger than 0.1 will also have a non-zero digit in the first place. So here the value must be 2 at irrational numbers. In between 1 by 100 to 1 by 10, the first non-zero entry must appear in the second place. So this must be, the value here must be 3. Again, at irrational. Here the value must be 4. And so on. Value must be 4, here must be 5 and 6, and so on. So as one can see, these sort of rectangles, let us observe that these rectangles formed by S escape towards infinity in height, but their width at the same time decreases. Decreases in powers of 10. Right? So the first one was 9 to the power 10, the width, but the second one is, it is 9 by 100. The third one is 9 by 1000 and so on. So the decrease of the width is in powers of 10. Okay. So from here we cannot really expect whether this is integrable or not integrable. All we can hope is, let us try to approximate it using simple functions. And we are expecting that once we approximate using simple functions, we are going to get these type of rectangles. Only now they will be solid rectangles. So even at rational points, we are going to get the same value throughout that interval, and then we can use geometry to find the area of the rectangle. So let us do the similar technique that we have been doing so far. Let us write Sn as k from 1 to n into 2 to the power n, k minus 1 by 2 to the power n, chi of f inverse k minus 1 by 2 to the power n to k by 2 to the power n, k by 2 to the power n plus n times chi of f inverse k minus 1 by 2 to the power n to k by 2 to the power n. Okay, so what we'll do, let us, because we'll have to do it analytically a bit before we move to drawing figures. Let us write x as follows: 0.A1, A2, A3, An, and so on. But this I can write summation k from 1 to infinity ak by 10 to the power k, where these ak's, they are either 0, 1, 2 up to 9. They are one of these digits. There is no other choice. Okay. Then what we do know is that fx is equal to n. Fx is equal to n. Yeah. I think I may have drawn bit shifted, because what we wanted was n whenever it is in the n plus 1th place. So this must be 0 rather than 2, it would be 0, and this would be either 1 or 2. 1 or 2. That doesn't really matter. So these rectangles would be shifted in the following sense. Let me redraw it. Since here the decimal expansion has a non-zero entry in the first place itself, so the image must be 0 here. So here it is 0. So in fact here it is 0 everywhere because rationals are already 0. Here it would be 1. Let me call this as 1 and this as 2. These are only at irrationals. Here it would be 3. Here it would be 2. Here it would be 3 and so on. So again, the observation still remains. Only thing is that the rectangle, the heights have shifted. So fx is equal to n if a1, a2, all the way up to an are 0, but an plus 1 is non-zero. Yeah. So what does this mean? If this is the case, then well, that is if, rather I can write if and only if, and of course x is a irrational number in 0, 1. If and only if this k runs from n plus 1 to infinity, ak by 10 to the power k, and x is in q complement intersection 0, 1, which is same as saying I can take 10 to the power n plus 1 common, and then I can write this sum k from 1 to infinity ak by 10 to the power k minus n minus 1. So notice that since ak is non-zero, oh well, again here it should have been, but is it? Yeah, I have not written it correctly. So once I take 10 to the power n plus 1 common here, the numerator becomes k minus n minus 1, but the denominator remains 10 to the power k, or rather it should in fact go from 0 to infinity. So with this understanding, what we do have is a k minus n minus 1 I'm so sorry. Today I'm making a lot of writing errors. This is k minus n only because we want to start it with a n plus 1. Oh, wait. So the first term should be n plus 1. So it should be k plus n plus 1. Yeah. So a n plus 1 is non-zero, implies that this x is actually bigger than 1 over 10 to the power n plus 1. But at the same time, it must be less than 1 over 10 to the power n, because all those terms are already gone. We are now in n plus 1th stage. So that means fx is equal to n if and only if x is an irrational number between 0 and 1, and or maybe I can combine this and I can simply write x is an irrational number between 1 over 10 to the power n plus 1 to 1 over 10 to the power n. Okay. With this understanding, let us now try to calculate what are these simple functions Sns, and now we'll see what actually happens here. So let us in general write f inverse of k minus 1 by 2 to the power n to k by 2 to the power n. This is the collection of all elements in in what? In R, such that fx lies inside this interval k minus 1 by 2 to the power n to k by 2 to the power n. Okay. So yeah. Moreover, this is non-empty if and only if this k minus 1 by 2 to the power n, this is an integer. Because if it is not an integer, then this whole small interval, it does not contain any of the integers, and therefore the values of f are only integers, right? So the pre-image must be integer. So this is non-empty if and only if k minus 1 by 2 to the power n is an integer. In which case, in this case, what we have is k minus, let me just write it directly, k minus 1 by 2 to the power n to k by 2 to the power n. This is equal to 1 over 10 to the power k minus 1 by 2 to the power n plus 1 to 1 over 10 to the power k minus 1 by 2 to the power n. Open here, because as we saw that f can assume this integer n if and only if x is inside 1 over 10 to the power n plus 1 to 1 over 10 to the power n. There is no other way. And of course, it should be an irrational. Okay. So now, what do we want? Ultimately, we want to find out. The integral of Sn, and this sum survives only for those k for which k minus 1 by 2 to the power n is an integer. Or what I can say, this is same as saying k minus 1 is m times 2 to the power n for some n. But notice that this is a positive thing, so or rather a non-negative thing. So it is m must be inside n union 0. Or what is the same? K is m into 2 to the power n plus 1 for some m in n union 0. Now it is easy to see that as k varies over 1 to up to n into 2 to the power n, m varies over for what values of this it can be. Not a lot of values, right? M can only vary over 0 to n minus 1. Because at n, the k becomes bigger than n into 2 to the power n. So we are not. So only these values of m are possible. And inside these values, what we have is Sn I can simply write m from 0 to n minus 1, m into chi of 1 over 10 to the power m plus 1 to 1 over 10 to the power m plus n into chi of, well, what remains that I have not calculated it yet, but let us try to write it, n2 plus infinity. So what is f inverse of n2 plus infinity? This is all the elements, especially the irrational numbers, inside 0, 1, such that fx is bigger than or equal to n. And if it is bigger than or equal to n, it means it can take the value n, n plus 1, n plus 2, and so on. So this could be any irrational number which is less than 1 over 10 to the power n. So this is 0, 1 over 10 to the power n. And one can notice that exactly this part is left. This should be open. Therefore, Sn is m from 0 to n minus 1, m into chi of 1 over 10 to the power n plus 1, m plus 1 to 1 over 10 to the power m plus n times chi of 0 to 1 over 10 to the power n. Now it is very easy to calculate what this is. Integral of Sn d lambda over r. This is m from 0 to n minus 1, m times the length of this interval, which is 1 over 10 to the power m minus 1 over 10 to the power m plus 1, plus n times the length of this interval, which is 1 over 10 to the power n. And what is this equal to? It is, well, multiply 10 here. So it is 9 by, let me just write it, 9m by 10 to the power n plus 10 to the power m plus 1 plus n over 10 to the power. And then, well, one can calculate this. So this is again same as, okay, let me calculate it for you. So 0 to n minus 2 I will write first, 9m by 10 to the power m plus 1 plus the n minus 1 term is 9n minus 1 by 10 to the power n plus n by 10 to the power n. So I can combine this thing. This becomes 10n minus 9 by 10 to the power n. Although, is it even helpful? What we want. But okay, even if I don't do that, let us keep it this way: 10n minus 9 by 10 to the power n. Notice that 10 to the power n grows much rapidly than 10n minus 9. So as n goes to infinity, this is going to go to 0. Now the other term is, I can write it as 9 into m from 1 to n minus 2, m over 10 to the power m plus 1. And if one knows the formula, this is almost of the form 1 by 1 minus x whole square, where x is 1 by 10. So limit n going to infinity plus 10n minus 9 by 10 to the power n. I keep as it is. Limit n going to infinity, integral Sn d lambda over r. This is equal to 9 into m from 1 to infinity, m by 10 to the power m plus 1, which is equal to, because this as n goes to infinity, this goes away, as we discussed it. This is equal to 9 by 10 cube, 1 over 1 minus 1 by 10 whole square, which is 9 by 10 cube into 10 square by 9 square. So 1 9 goes away, 10 square goes away. What remains is 1 by 90. So as one can see, this function, which is not very easy to see, it is not very easy to visualize. This f is inside L1. It is a non-negative measurable function, of course. It is inside L1, and it is the value of integral of f is 1 by 90. And integral f d lambda over r is 1 by 90. Okay. So this was all about integrating non-negative functions. Now let us look at a few things that were sort of left in the class. One of the things that was left was density of the Riemann integrable functions in L1 functions. It is not very difficult to see, yet one must look at least the arguments. The formal proof can be written by themselves. So density of the space of Riemann integrable functions on a closed bounded interval AB inside L1 of AB. So first of all, what do we mean by density? I should give the definition as well. In a metric space, XD, where D is the metric, a set S of X is dense in X if for any point in X there is a sequence Sn in S such that Sn converges to X in the metric D. Or equivalently, what some people say is that every point of X is an accumulation point of S. Oh, I'm sorry, it may not be accumulation point, it is a limit point of S. So one of the easiest example is the set of rational numbers in the set of real numbers that is dense with respect to the usual metric of absolute value. Irrational numbers are also dense in real numbers with respect to the usual metric of absolute value. What we want to say is that the space of Riemann integrable functions is dense in the space of Lebesgue integrable functions on closed and bounded intervals. we have already seen a few things. We have seen that RAB sits inside L1AB. So that is not a problem. What we want to prove is that every function inside L1AB, that is actually a limit of a sequence of Riemann integrable functions. But that is also not very difficult to see, because if we start with f in L1, then f can be written as f plus minus f minus, and both f plus f minus, they are non-negative measurable functions with the property that integral of f plus d mu, or here we have d lambda ab, this is finite, and integral of f minus d lambda over ab, this is finite. Now, what we will do, since they are non-negative measurable functions, there is a sequence of simple functions Sn and Sn prime that converge to f plus and f minus. So, well, so there exist sequence of simple functions Sn and Sn prime. So they are also non-negative simple functions indeed, such that Sn converges to f plus, Sn prime converges to f minus. Now what do we know is that also limit integrals Sn over ab d lambda, this is equal to limit ab, limit n going to infinity, integral over ab f plus d lambda, and why did I write limit here? Then not limit here, and then integral Sn prime d lambda over ab. This is integral of f minus d lambda over ab. So since Sn and Sn prime, they converge to f plus and f minus, one expects that Sn minus Sn prime converges to f plus minus f minus, which is f. So Sn minus Sn prime converges to f plus minus f minus, which is f pointwise. But does this mean that this converges inside the metric of RAB or the metric of L1AB? No, right? Because the metric of L1AB requires integration. So in that case, we'll have to actually check whether integral of mod of f minus Sn minus Sn prime d lambda over this integral AB, this is 0, or this converges to 0 as n goes to infinity. But it is easy to see. Why is it easy to see? Since f is in L1 and Sn minus Sn prime, they are less than or equal to f everywhere. Well, less than or equal to f in the sense Sn primes, they approximate f minus from below, and Sn's approximate f plus from below. So they are in between the x-axis and the image of f. So I can write this integral over AB of f, mod f minus Sn minus Sn prime d lambda as integral over AB f plus minus Sn prime d lambda, f plus minus Sn d lambda minus integral of f minus minus Sn prime over AB d lambda. So individually they are Lebesgue integrable functions, and the space of Lebesgue integrable functions is a vector space, so we can split it up. That is not an issue. But now what happens? Individually these integrals go to 0. Therefore, by limits of the calculus of limits of sequences, this goes to 0 as n goes to infinity. And hence, Sn minus Sn prime, they converge to f in the metric of L1. But now we still don't know whether this sequence convergence is from RAB. Can we, is it easy to see that it is in RAB? Yes, because Sn minus Sn primes, they are all step functions. Hence, they have only finitely many discontinuities. Many discontinuities. Which means Sn minus Sn primes, they are in RAB for each n. And therefore, RAB is dense in L1. This was one of the points that was left during the lectures, and I hope that this makes the theorem clear that L1AB is a completion of RAB. And why is it called a completion? Because that is how completions of metric spaces are defined. Let me give that definition as well. So let XD be a metric space and okay, a complete metric space YD prime. This is a completion of XD if, of course, Y is complete, that I have already assumed. If there is a injective isometry, isometries are automatically injective, so I did not write it. If there is an isometry I from X to Y such that IX is dense in Y. So why do we require this? Notice that we could, just keep on putting more and more elements and we could make it complete. For example, one of the completions of Q is R, that is fine. But who is to guarantee that we are not going to add any more elements? We could add more elements and make it C, right? The whole complex plane, that is also a complete metric space with respect to the absolute value. And it contains the set of rational numbers. So we really don't want to go that big. We want to stay as close to the given set X as possible, which is why we say that the completion of a metric space is the sort of the smallest complete metric space, in the sense that once we complete X, X becomes dense in Y. So one of the easy observations is that if XD is complete, then X is a completion of itself. That is because it is already a complete metric space, and the identity map from X to X is such that it is an isometry, because there is only one space, it preserves the metric, of course, and moreover, X is dense in itself. In fact, every space is dense in itself. So, okay. So with this, let us do one more thing, and then we will stop. There was another thing that is under question. Why do we require even the completion of RAB? Question. Why do we require the completion of RAB? Does that mean, or equivalently, does that mean RAB is incomplete? So can we find a Cauchy sequence in the space of Riemann integrable functions which does not converge to any Riemann integrable function? So that does happen. Let us look at this particular example here. Let us define Gn from 0 1 to 0 1, or rather 0 1 to r, as gnx is, I'll directly write it, minimum of n comma minus log x. So the first question is, how do these functions look? So let us try to figure out at least a few elements of this sequence. Let us try to write g1, g2, g3, and perhaps g4. We will get an idea how these functions look like. So g1x, so minimum of 1 comma minus log x. So it will be 1 if 1 is less than minus log x, or equivalently x is less than 1 by e. And it is minus log x when x is bigger than 1 by e. What is g2x? It is minimum of 2 comma minus log x. So this time it is 2 whenever minus log x is bigger than 2 or x is less than 1 over e square. So it is 2 when x is less than 1 over e square, and it is minus log x when x is bigger than 1 over e square. g3, this is 3 when x is less than 1 over e cube, and again it is minus log x when x is bigger than 1 over e cube. g4, it is 4 when x is less than 1 over e to the power 4, and minus log x when x is bigger than 1 over e to the power 4, and so on and so forth. Let us try to draw them. This is 0, here is 1, and since we are doing it up till 4, let me 1, 2, 3, 4. Okay. So notice that here we have 1 over e square, 1 over e cube, 1 over e to the power 4. So 1 over e, 1 over e square, 1 over e cube, 1 over e to the power 4, and so on. So g1 takes value 1 when x is less than or equal to 1 over e, and then minus log x when x is bigger than 1 over e. So notice that first of all, all these functions are continuous. The continuity is not a problem. What happens when x goes towards 0? Well, here in all these functions there is no problem. But when x goes, like if I look at only minus log x, then towards 0 it is going to be unbounded. So that is not going to really work. And towards 1, this towards 1, at 1 actually this all these g's become 0. So the first function is 1 from 0 to 1 by e, and then it just comes down to 0. The second function is 2 from 0 to 1 by e square, and then it comes down to 0. Notice that it matches the first function here. The third function, it is 3 from 0 to 1 by e cube, and then it comes down using minus log x, and then it matches the previous functions. And the fourth function is 4 from 0 to 1 by e to the power 4, and again it comes down using minus log x, and then matches the previous functions. So all in all, as one can see, these rectangles get smaller and smaller in width, but their height keeps on increasing, and the function sort of takes the form of minus log x as we increase our n. So first claim is that Gn converges to minus log x as n goes to infinity pointwise. And it is easy to see, since 1 over e to the power n converges to 0 as n goes to infinity, for each x in open 0, 1, open 0, closed 1 in fact, pointwise almost everywhere, because at 0 there is going to be a problem. So for each x in open 0, closed 1, what will happen? There will be some stage n naught such that 1 over e to the power n naught is less than x, and therefore for each n bigger than or equal to n naught, 1 over e to the power n is less than x, and hence Gn at x is minus log x for every n bigger than or equal to n naught. So at least Gn so at least Gn is converges to minus log x pointwise almost everywhere. And one can redefine this minus log x at 0 to be any arbitrary value. In the final integral, it won't really matter. But minus log x is not a bounded function. Therefore, minus log x is not inside RAB. Because by definition, the space of all Riemann integrable functions must be bounded. And there is a result which says that they must be also continuous almost everywhere, which we have not seen. Perhaps we'll see it next time, or where it is given in the book. Okay. But now there are two questions. First of all, is this Gn a Cauchy sequence? If it is a Cauchy sequence, how do we know that it does not converge to any other function in the L1 metric? Because we have only proved it converges to minus log x pointwise, right? How do we know it does not converge to any other function? So, oh well, yeah. First, I have to prove that Gn is Cauchy sequence. So let us look at integral of mod Gn minus Gm d. Well, yeah, okay, d lambda I can do over r. Or what is the interval? Interval is 0, 1. So this is going to be split into 3 parts. 1 over e to the power n, assuming that n is bigger than m. 1 over e to the power n minus m dx or d lambda x minus integral of 1 by e to the power n to 1 by e to the power m minus log x minus m dx plus integral 1 by e to the power m to 1 minus log x minus log x. As I said, after a certain stage they are equal. So this is the stage where they are equal. Oh, I'm so sorry. Something happened. I was sorry about it. Yeah, this is dx, and this just cancels off. So this integral doesn't play any role in mod of Gn minus Gm. What remains is n minus m over 1 e to the power n plus what is the integral of log x? It is x log x minus x. So minus 1 over e to the power m log of e to the power m minus 1 over e to the power m minus 1 over e to the power n log of e to the power n minus 1 over e to the power n oh, sorry. Minus m times 1 over e to the power m minus 1 over e to the power n. Again notice that, so okay, let me just write it first. N minus m by e to the power n minus, this is m minus 1 by e to the power m minus n minus 1 by e to the power n minus m times 1 over e to the power m minus 1 over e to the power n. So as nm go to infinity, exponential grows faster than all polynomials. Grows faster than all polynomials. Therefore, this limit nm going to infinity, this whole expression is going to be 0. And hence, Gn is a Cauchy sequence with respect to the L1 norm, or well, let me not call it norm, L1 metric on RAB. Okay. Now coming to the second question, we have proved that it converges to minus log x pointwise or almost everywhere. How do we know that it does not converge to some other function in the L1 metric? So let us assume that it does converge. Let Gn converge to F in L1 metric. What does it mean? It means integral of mod of F minus Gn d lambda over this interval 0, 1. This converges to 0 as n goes to infinity. But this is a non-negative function. So this can only happen when the integrand becomes 0 as n goes to infinity. Or rather, well, not the whole integrand, but there is a sequence. Therefore, there is a subsequence gnk of gn such that mod of gnk minus f converges to 0 almost everywhere as k goes to infinity. So, and why is this true? This is true because mod of f minus gn, this is bigger than or equal to 0, and this type of sequence can go to 0 only if there is a subsequence which goes to 0 of the integrands. Perhaps we'll see this in one of the lectures later. So for the time, assume it. If it is not covered in the lectures, we will definitely do it towards the end of the course. Now, what does it mean? It means that GNK converges to F pointwise almost everywhere. But pointwise limits are unique. Therefore, F must be minus log X, which is not in RAB. Yeah, this is also almost everywhere. And hence, we have that RAB is not complete. Okay, so with this, perhaps we can stop for today. These were some facts about whatever is being discussed in week 9, that is the properties of Riemann and Lebesgue integrals. And well, we have not touched product measures yet. I hope to do it in the next time. So I'll give you 1 minute. If anybody has any questions, you can ask. The YouTube audience can ask using the live chat, and I will answer them. So at 8:15 we'll stop. Okay. So if there are no more questions, let us stop. We'll meet next Friday with week 10 discussion, and I hope to cover some examples of product measures, and if the integration on product spaces is done, then some examples of that as well. So okay, let us stop now. Thank you.